Hey everyone, I hope you found week one's Action Center video at least somewhat helpful, and so I'm going to try to do the same thing again with this one. And so I've chosen the three questions that I think are the most important from this Action Center and concepts that you should be very comfortable with moving forward. And so this first one is asking us about a percentage of leucine molecules in a Zwitterion form. And so to answer this question, like you'd first want to do two things, I think, which is number one, you'd want to draw leucine, or at least be able to picture it. And number two, you'd have to know what a Zwitterion is. And so leucine, in one of its protonation states, would look like this. And of course, it's only got two pKa's because this is not an ionizable side chain. And so in this state, it's not going to be a Zwitterion because a Zwitterion is defined as something that of its protonation states would have a neutral charge. So here the positive aminium and the negative carboxyl charges would cancel each other out and you'd be left with a neutral molecule. And so if they're saying that the two pKa's, so the pKa of this carboxyl group would be 2.33, and this one would be 9.74, what percentage are in the Zwitterion form at pH 2.3? The aminium group is so far away in terms of pKa from 2.33 that we don't need to worry about it, in the sense that we can assume that all of it is protonated because the pH is low enough for it to do that. Now, because the carboxyl group is at the pH that's equal to its pKa, we know that it's going to be half protonated and half deprotonated. And so if that's the case, then, half of them would exist in this deprotonated form that I've drawn here. So then we could say that it's going to be 50% of the leucine molecules that are going to be in the Zwitterion form. Now this one asks about the average charge of the amino acid aspartate at pK2. So this is one of the ones where, you'd have to use that mnemonic and you'd recognize that aspartate is an amino acid with an ionizable side chain, so it's going to have a third pKa, which we designate as pKr. And so that pKa, I think you'd have to memorize these, all of the ionizable side chain pKas. But essentially, for this one, the pKa of the R group, I don't remember exactly what it is, but it's going to fall between the pKa of the aminium and carboxyl groups. So the way that I like to do these problems is I'll draw aspartate first. Which looks something like this. And I'll draw it first as if I was drawing it at pH 0. So at this pH of 0, everything is going to be protonated that can be protonated. So I've got this protonated and these as well. So once we get to our pK1, once the pH reaches that point, pK1 refers to our our carboxyl group here, which is going to be around 2 point something, I think, if I'm remembering it properly. So that's going to be the H that's going to deprotonate first. So once that happens, this molecule over here is going to have a net charge of +1. This one will have a net charge of 0. Now, before we get to the pK of the aminium group, which is pK2, we'll have our pKr. And you don't need to know what that pKr is for this question you don't need to know it exactly, But for questions in the future and just for this class in general, you should have the actual values memorized. So once we hit our pKr, the iminium group is going to stay the same. We've already deprotonated this carboxyl group, and now we can deprotonate the side chain. And so this is going to have a net charge of -1. Now we've hit our pK2, which is going to deprotonate our iminium group. So we'll be left with H2N. And these would stay the same in their deprotonated states. And so this is going to have a -2 charge. And so the question asks, what's the average net charge at pK2? So at pK2, you would be averaging this charge and this charge. So it'd be -2 plus -1 divided by 2, which is going to give us -1.5 as our net charge. Now this question is kind of tough. It's kind of weird to get used to this kind of reasoning when you first see it, but this is something that's going to come up a lot in this class, so I would recommend that you get really familiar with this. Now, something that I struggled with when I started these was I would always try to think about these in terms of amino acids, but you don't necessarily need to do that. So you don't need to force yourself to draw an amino acid and pretend like, oh, it has two amino groups or 2 carboxyl groups or whatever the question says it is. You can just draw whatever little amorphous structure you want to, and it's got 2 iminium groups that I'm going to put right here, and 1 carboxyl group that I'll put right there. And it doesn't really matter where you put these either, it's all arbitrary. So, you know, these have pKa's of 8.7 and 10.2, and the carboxyl group has a pK of 3.8, and the whole thing is at a pH of 6.5. Now, what this pH tells us is that we've essentially drawn the molecule correctly as it is right here in terms of charge, because each one of these pKa's is greater than 2 units away from that pH, so we can assume that all of them are going to be either fully deprotonated or fully protonated. So the iminium groups are, the pH is 2 units less, so we can assume that all of them are protonated. The pH is greater than the pK of the carboxyl group by more than 2 units, so we can assume that it's all deprotonated. And now all we have to do is figure out the pH once we add the HCl. So we know that we've got 100 ml of this, of a 0.1 molar solution. And if we do the conversion, because we want to work in moles ideally, this is going to be equal to 0.01 moles of this compound. And then we added 40 ml of 0.1 molar HCl, which is going to be equal to adding 0.004 moles of HCl. Now, the important thing is that this HCl, this is the same thing as, like, the only thing that we care about is that this is functionally the same thing as adding 0.004 moles of H+, because that's going to dissociate in solution. So we care about what this H+ is going to do. And this H+ is going to protonate anything that it can in order to lower the pH of the solution. And so the only thing that it can protonate is this carboxyl group. So that's what we care about in this problem. So the way that we can actually solve for the pH is using the Henderson-Hasselbalch equation. So pH is going to be equal to pKa plus the log of the basic form over the acidic. And so what we're doing is we know that we've started with this 0.01 moles of everything. And what we're doing to that 0.01 mole, because there's also, what that means is that there are 0.01 moles of this carboxyl group. And that's really the only thing we care about here, because that's the only thing that's getting changed. So we can say that the pH is equal to the pKa. The pKa is going to be the pKa of that carboxyl group, which is 3.8, plus the log of the the basic form, which is going to change because we're losing this much of the basic form. We're losing that 0.004 moles of the basic form that are going to be converted to the protonated form. So this is going to be our 0.01 moles minus the 0.004 moles that are going to be converted to our HA form. And since we had no HA to begin with, the 0.004 moles that we create are going to be the only HA we have. And so once we solve this equation, we're left with about 3.97, which you can round to 4. So the pH would be 4.0.